Hello, I'm Federico Alba, engineer and technical director of ATyges, and DJI Enterprise solution engineer for Geospatial. Today I'm in Cádiz in southern Spain at one of the most famous bridges in Cádiz, La Constitución de 1812 Bridge, one of the highest bridges in Europe, with a gauge of 69 meters and a total length of 5 kilometers. We are today here to create a digital twin of the bridge. This bridge is critical infrastructure. Every day it faces traffic, wind, and weather. To keep it safe, engineers need accurate and up-to-date data. That's why we are creating a digital twin. A digital twin helps monitor deformation, detect issues early, and create a solid baseline for future inspections. In this video, I'll show you a complete workflow to capture a high-quality digital twin using the DJI Matrice 400 L3 lidar, including mission planning, flight execution, lidar processing, and final results in DJI Terra. For lidar flights, accurate RTK data is essential. First, we set up a DJI RTK3 multifunction station as a local base station. This avoids connectivity issues with external Core S networks and keeps the baseline short, which improves accuracy. Once the station is on the tripod, we power it on and confirm it is in base mode, indicated by the green LED. Using the DJI RC2+, we connect the Matrice 400 to the DRTK3 station, calibrate the base position, and confirm the RTK status is fixed. While the base station is recording data, we establish ground control points. For this, we use a second DRTK3 in rover mode, connected to the base station for maximum accuracy. The rover mode is confirmed by the yellow LED, and points are collected using DJI Enterprise Android software. Once ground control is complete, we power off the rover and begin the lidar flight with the Matrice 400 and Zenmuse L3. Next, we move into Pilot 2 to create the flight route. In the flight route library, we create an area route and adjust the main parameters. Sampling rate is set to 100 kHz. DJI L3 can support maximally 2 million points per second, but in order to achieve a larger flight range, we will choose 100 kHz. We select non-repetitive scanning to capture the bridge from multiple angles and set the overlap to around 70%. The course angle is set to around 170 degrees, creating a U-shaped flight pattern that works well for long linear structures like bridges. Once the route is completed, it is saved within the project and linked to the DJI account. The route is now fully integrated into the workflow and ready for flight. Before takeoff, we check the pre-flight screen to confirm system status, RTK fix, sensor behavior. Now it's time to fly. The Matrice 400 automatically follows the planned route while collecting lidar and RGB data at the same time. During the mission, we continuously monitor different views, including lidar and RGB, to make sure coverage is complete. The Matrice 400 allows us to see in real time through the sensor, in our case the Zenmuse L3, as well as through the 4 FPV cameras, so even though the lidar is always looking towards the ground, the pilot can see in all directions in which the drone is flying, making it easy to control the safety of the operation and any interference that might arise from external elements. If anything unexpected comes up, we can immediately stop the mission and take manual control. For complex areas, especially underneath the bridge, setting another flight route may be required to capture data that automated routes can't reach yet. After completing the data collection, all datasets are imported into DJI Terra. A new lidar project is created, and the folder containing the captured flight data is selected and loaded into the software. The coordinate system is then adjusted to match the local reference system used for the project. Next, the ground control data collected with the DRTK3 system is imported. This includes both ground control points, GCPs, and checkpoints. In this workflow, 3 points are used as control references, while 9 additional checkpoints are reserved exclusively for accuracy validation. Processing parameters are then configured. Optimization, accuracy enhancement, and smoothing options are enabled, and the point cloud density is set to high. The reconstruction outputs are selected, including orthophoto generation, 2D maps, a 3D mesh model, and Gaussian splatting reconstruction. Once all parameters are confirmed, the reconstruction process is started. After several hours of processing, the final results become available. The generated point cloud clearly reveals fine structural details of the bridge, including cables, tension systems, and overall geometry. Alongside the point cloud, a high-quality 3D mesh and Gaussian splatting model are produced, providing detailed and visually accurate representations of the structure. The quality report is then reviewed to verify accuracy. After approximately 5 hours of processing, the reconstruction achieves a root mean square error of about 2 centimeters, with ground control point errors below 7 millimeters, confirming high precision. DJI Terra produces multiple outputs, including DOM, DSM, point clouds, surface models, and Gaussian splatting data, all of which can be exported for use in DJI Modify or other third-party engineering software. And that's the complex workflow for creating a high-quality bridge digital twin, using DJI Matrice 400, L3 lidar, DJI-3, and DJI Terra and Modify. From here on, this model becomes a long-term reference, something engineers can return to, compare with future data, and use to support decisions. This is what digital twins are really about, turning reality into reliable data.